So today I'm gonna just review the most of the things that we discussed, in this class, and some of the things that we didn't have to talk about. So quickly go over them as well. If we have time, we will probably go over the quiz 1 and quiz 2 as well. And then if we have more time, we will just answer some of the questions that you might have. All right. So that would be the plan for today. Okay, any question, anybody on Zoom? Can you hear me well? Okay, great. All right, so we talk about the logistics of plan on Wednesday. What we're gonna do is go over the presentations. I think since we have 4 presentations or 5 presentations, it's gonna probably take you a little bit longer. Afterwards, I'm just gonna talk about final project and your final quiz on Wednesday as well. So as I said, things we discussed so far and other things that are important for we didn't have time to talk about, and then just very quickly over what comes next. So I mean, I started this course with just talking about the status quo, right? So what we are doing so far in terms of computer security. And what I said was basically what we did so far was we think about security as kind of like an after the fact or second order issue. And the reason for that was there were other metrics that was really important for us, especially in terms of competition with different companies, and also the challenges that we always had that made the security always a second order factor. The problem though is that nowadays, that given that cyber security becomes a major threat and people can actually see the actual impact of, for example, being attacked, now people are now thinking about, okay, the strategy of putting the security in the back burner and not really care about it as the first order issue no longer works. So we need to kind of actually come up with some at least basic ways of defending our systems and making our systems secure against this type of attack. So that's what we are here, where we are right now, that we're kind of on the edge between not caring about security and caring about security as one of the key issues in our computer systems. And the reason that we are kind of like, we are shifting toward that is, as I said before, is because that computers are becoming more and more critical in our everyday lives, right? It's actually, as you can see, it's becoming attacking systems and attacking computers, becoming a weapon for even for states, right? So if you want to attack a country, you no longer need to, just physically attack them. You can virtually and cyber using a computer or a cloud system, you can attack those systems, right? So that's where we are and where we are heading. So because of that, now we need to think about, okay, how do we secure systems, right? And as you have seen in this course, we said that essentially it's mostly about the assumptions and the principles that we have, and then the next steps is really implementation of those assumptions and principles. So in every situation that we discuss in this course, we always look back and say, okay, what is the threat model? What are the assumptions that we make? What are the important information that needs to be secure? What are the adversaries, interest and things that the adversary values for it? And what are the adversary's capabilities, right? So these are the main things that we always thought about. And then there were a long list of principles that I discussed at the beginning of the course. And then recurrently you saw that you actually keep using them, like defense in depth, least privilege principle, or distributing the trust, and all those things that we kind of at every stage of this course, you've seen that we kind of either directly or indirectly use those kind of those principles. And then if we follow those principles, we usually have security. One thing that so I didn't put here, but I want to add here is the implementation. And the issue is that, of course, we can have assumptions and principles, but part of the issue for security also comes from the implementation side. And sometimes, the bugs introduced during the implementation or the mistakes that we might make during the implementation can also create security bugs. So it's not just all about the assumptions and the principles. The implementation is also another key part that we need to be aware of, right? Then we basically said that in order to fix this issue, what happens is basically the security becomes kind of a game theory kind of in some sense, where we want to minimize our overheads and our costs, right? So, and then on the other hand, we want to maximize our profit, which is the security in this case. So it's kind of becomes a trade-off between security, performance, most importantly, cost. It could be energy. It could be many other things, right? Like time to market or design complexity. So there could be many of these things. And the objective here is kind of like coming up with solutions that gives us this security, but doesn't sacrifice, these other metrics significantly. So we cannot, for example, say, yes, there's this amazing solution that will completely ignore and remove, all the side channels that we have, but that means that your battery power would be 90% less than what you have right now. Right? This obviously has its own issues because, battery power and energy, energy is also one of the key components of your system. We cannot completely, ignore that. Of course, this always depends on the application. So for example, if you're talking about a military application, then we can say, okay, security is the primary factor. But generally, when we are talking about computer security, we are talking about user level and normal people level security, right? So we are talking about normal cell phones and computers and laptops and so on. So when we're talking about this, it's just combination of all of these things that matter. So we cannot say, okay, we only focus on this or that. And that was exactly the problem that we had before, right? So we always ignore security and talk about all these other metrics. What we are saying is that we are actually now should be doing have a holistic approach of all of these different methods. And that's the way to move forward, right? So as a security researcher, the challenge is really coming up with real solutions that are effective, but doesn't really sacrifice all of these challenges. And then another game that needs to be played is kind of convincing companies and stakeholders and governments to pay that price, because security is not free, right? So you have to sacrifice something. And as I said, in the past, usually the sacrifice hasn't been justified. People usually say, okay, security is a second order issue, so we don't have to be worried about. Now the momentum has been shifted towards security, right? So now you can more easily justify why we need security, but still we are, as I said, we are on that edge between that people still think that security is not a major challenge in some cases. So that's another, issue and another consideration that we need to make. Any questions at this point? Okay, so let me quickly go over things that we learned. Basically, as I said at the beginning, we're kind of like, had a cross-layer format of what we have learned. We kind of started from the bottom to top in some sense, but at the hardware, the things that we discussed was mainly hardware Trojans and supply chains that we discussed last week. We said that, supply chain is becoming more and more of an issue these days, mainly because of the conflict that exists between countries. We also talked about Trojans, these modifications to the hardware, and what would be the impact of these modifications. I gave you some real examples and real attacks. I also talked about how we can fix these issues, right? So for example, if we can use side channels or we can use changing the way that we are manufacturing the system, that can help us to improve the systems and make it robust against Trojans. Then we extensively talk about kind of like the intersection between hardware and architecture. Side channels was the main example. We talked about physical side channels. It's kind of like, because of the activity of the different applications and program that we have, we are seeing the signals from the outside of the system. We can collect this, and that can kind of like break those assumptions that we have. And because of that, these days, if you are making any assumption, we also have to consider side channels as one of the possibilities. So we cannot just say, oh, side channels are out of scope. We need to also think about like what are the side channel scenarios for the attack, right? We also talked about secure boot and how do we, base our trust on hardware. We start our trust from hardware, and then we talked about, root of trust and dynamic root of trust and chaining this trust layer by layer until we actually fully load a piece of software, which was the operating system. So we gradually start from pure hardware to pure software in step-by-step format. So that was kind of like, where we boot our systems and where we put our trust. Then we talked about architecture and system, intersection. Trusted execution environments, one of the key things that we discussed, right? So trusted execution is actually becoming more and more popular and important these days. And the reason for it is because of the sheer number of applications that trusted execution environment can give us. Mainly because of the new functionality, the new applications that trusted execution kind of unlock for us, such as being able to remotely execute things without the need to trust that server. So this notion of platform as a service or server as a service is actually coming from, or infrastructure as a service. Infrastructure as a service is actually coming from this fact that you don't necessarily need to be the owner of the device that you want to run your program. You can, for example, use an infrastructure somewhere else in the world, such as a server for Amazon Web Services or Microsoft Azure, and all you need to do is being able to remotely upload your code onto that infrastructure, onto that computer, and then you can just freely run things in the trusted execution environment, right? So with this scenario, the owner of the computing device never really knows what's going on inside your system. On the other hand, it gives assurances to the owner that nothing else about the system will be leaked through that program. And then it's also give you assurances that your code and your data will not be leaked and will not be used by the owner. So it's kind of like a win-win situation for both the user and the service provider. And in terms of cost, is also beneficial for both parties, because the service provider such as Microsoft or Facebook or Amazon has the capability of creating these massive data centers with low cost. Whereas for us as a usual users, you cannot really afford to have that. There's lots of overheads that comes with it. So it would be beneficial for us to actually upload our code there. It would be beneficial for them to provide that service. They can just always, charge a small amount of money, something that's, higher than their cost for maintaining the system. Would be, useful for them, would be useful for us, and so on. And the issue of the security and privacy can always be addressed by the T. So that's why T becoming a more and more interesting and important use case, because it's essentially there's this entire market of infrastructure as a service. And then also there's machine learning as a service, there's software as a service, and all these things as a service concept kind of driving the need for trusted execution environments. And then we talked extensively about memory safety, and then we said, you have a question? No. We talked about memory safety. We talked about why we have memory safety issues, and generally we said that this is the main issue, the main security concern in our systems, because that's kind of like the gateway from the open world inside our computers, really. So most of the other attacks that we talked about usually starts with some sort of memory vulnerability and memory safety issue. So, I mean, it's one of the oldest problems in computer security. There is some fundamental issues that we cannot really fix this issue. There has been always, as I said, this arm race between the attackers and defenders in order to fix this issue. But I mean, the problem still remains as one of the key and most important issues in computer systems. Then I gave you two, system level end-to-end kind of, examples. Extensively, we talked about machine learning as one of the key systems that, security and privacy could be an issue for it. Most of part of the first half of the quarter, we talked about various issues in machine learning. We talked about the issue of adversarial samples, the inputs to the system, and we said that a good understanding of the systems could help the adversary to actually craft some samples that fool the systems. This could happen during the training, which we refer to as poisoning attacks, or could happen during the inference, we usually say evasion attacks. We then also talk about the machine learning as an object, as a piece of software as well, and say that essentially this becomes an IP, intellectual property of the designer, of the owner of the system. So there could be various issues, privacy issues and security issues in that system. So model extraction, membership inference, and model inversion was the different examples of that. And then we switch extensively to talk about privacy as an issue. And as I said, for this as a service systems, which machine learning as a service is kind of one of the examples, generally the privacy becomes an issue. And we talked about privacy preserving computation as a way to secure this. We talked about homomorphic encryption, multi-party computation, and of course, talk about the T's as one of the ways of talking about this. And then very recently, we talked about cyber physical systems. And as I said, this was the main focus of this course, essentially, where the system is kind of compromised of some sensing, some local processing, some networking, some cloud system, and some actuation. So these 5 components really build what is called a cyber physical systems. And essentially, the attack can happen in any of these layers, right? So adversarial samples, for example, is an example of an attack that can happen at the sensor side. Local processing attacks could be things like memory safety or side channels. Networking, we didn't really extensively talk about, but there could be lots of networking, such as man-in-the-middle attack or privacy attacks and so on. About the cloud, their attacks could be things like, digital side channels attacks or fault attacks or attacks to the trusted execution environments. And for the actuation, of course, the attacks could be anything that's, changed something in the real world, such as, for example, things we talked about the evasion attacks where we force the system to think that this is not a stop sign, it's something else, right? So there could be various ways of talking about this, and it's very actually interesting. All these layers have its own challenging problems. And as I said, since we're talking about system, whatever decision and solutions we come up with has to fit nicely into the system. So the cost is important, the feasibility of the solution is important. So you have to have a holistic approach when you want to talk about security of the systems. Okay. And then, as I said, an emerging issue in computer security is privacy. In the past, privacy hasn't been that issue before. And the reason that privacy all of a sudden becomes an important issue, as I said, is because of the cloud computing and the concept of infrastructure as a service. So these two things are kind of like the main 2 reasons that privacy all of a sudden becomes an issue, because there are services collecting this information, and in return of collecting that information, they gave us services. But the problem really these days is that how we can use these services without actually selling our data to them, right? So what we want to really do is kind of like, a balance between, at least we either have to know exactly what they're collecting, or they have to pay to us some money because of that. There should be some notion of, governance over the data, over the private data, and that kind of can help us fix the issue. I mean, as the solutions, we talked about privacy preserving computation, right? As I said, things like homomorphic encryption or multi-party computation. Of course, this is at the very early stages. So the main issue of that is performance, right, and the latency. But we are actually improving things. So this is like kind of, you're talking about less than 10 years of researching in this domain. So we are kind of like getting there and improving this. Another area that we really didn't talk about was in terms of policies. So one thing that will fix the issue of privacy is not just, coming up with technologies that help us, do the computation. It's also the policies, like what each company can collect and what each company cannot collect. What is the issue of, data owner? Who is the data owner? When we are talking about the ownership, what do we talk about? Do we talk about, raw image, or do we talk about the inference from that image? What we exactly we're talking about? So there's actually a huge amount of research going on the policy side of the things, on the law side of the things as well, which is quite interesting. So if you're like not into that much into, the technical aspects, with more of like, the impact and high level aspects, you can actually take a look at this type of in this line of work as well. So these days, lots of people are actually working on this domain as well. So now this is kind of like, what are the things that we discussed so far in this course? There are a few other topics that we didn't have not much time to talk about. So I want to just quickly go over them and talk about them as well. Is there any questions, anybody? Okay. So we didn't really talk about operating system security, or it's kind of like, operating system, of course, it's the bridge between the software and hardware. And it's kind of like, since it's kind of sits in between software aspects of things and hardware aspects of things in terms of security is very important. We briefly mentioned things that are relevant to operating systems, such as, the trusted execution environment was the key bridge between them, but we really didn't go into the details of, like, for example, what are the issues in operating systems that we need to be worried about, what are the solutions, and so on and so forth. So, I mean, the key challenge about the operating system is that we are facing a wide range of systems, right? So we are seeing servers and PCs, we're having mobile devices, IoT devices, real-time systems, firmwares, bare metal systems, and so on and so forth. So actually, the solutions that we come up with may not be necessarily applicable to all of these systems, right? So similar to the hardware solutions that we come up with, that doesn't fit really on one system. Same issue happens with the operating system as well. So any sort of solutions has to have this in mind when we are talking about solutions. And then we also talked about the issue with when the operating system cannot be trusted, and then we talked about the trusted execution environment. And again, given that trusted, securing the operating system is really difficult problem, trusted execution environment becoming more and more popular. There's also another line of research in the operating system, and that's reducing the trusted computing base, or TCB. So instead of like trying to make sure that the entire operating system can be trusted, the idea is that let's start with very small, computing base in terms of software, and then build our operating system kind of around this trusted computing base. So similar to the way that we start with the hardware and build on top of it, for building a trusted and secure operating system, what we can do is we can start with a small piece of kernel code that we can maybe examine thoroughly and run lots of tests manually in order to make sure that this part can be trusted, and then expand this into the full-fledged operating system based on that. So lots of research also going on into that direction these days. So another thing that we didn't extensively talk about was memory safety and security. We talked about what is the issues. We talked about buffer overflow and return oriented. but we didn't really go into the details of like, actually implementing one of these things. Maybe in future offering of the course, we will do some projects on things like return-oriented programming or buffer overflow. But if you're interested, there are lots of, interesting examples and tutorials out there that you can easily find and play with it. So my suggestion to you is actually trying to do something like a is try to implement the real control flow hijacking or real data only attacks and see how they works. We didn't have the time to go through them, but that would be an interesting project to do if you're interested into it. And one more thing that we kind of didn't discuss was like software security in general. We kind of talked a little bit about things like fuzzing and symbolic execution. And we said that essentially the idea of software security is two things, is using either, by design principles. So there are some principles that we kind of need to follow. The same way that we follow those principles when we are, for example, building our systems. And the second thing is detecting those bugs, right? We slightly talk about these detecting parts. We talked about symbolic execution and fuzzing, right? We didn't really talk about this principle. So that would be a course for itself of like, what are the correct principles when you're designing a software? So it's more of like a software engineering issue, but you have to know that there are principles that we need to follow. So as I said, tools, rules, and lots of testing. So that's usually what you will see in a proper software engineering course. Another key components of software security is programming languages. So there are actually programming languages that's uniquely designed to, for example, remove the issue of things like buffer overflow and so on. So there are type safe and safe languages specifically designed to solve these issues. Again, since we didn't have time to go through the details of software, engineering and software development, we really talked about this. But if you want to learn more about that, this is also a very interesting area of research and knowledge. Any questions on Zoom? Okay, good. And as I said, the second part is really detecting this. Again, this is also very extensive area of research. What are the analysis tools to detecting these vulnerabilities? How to run tests, especially for huge and large scale software systems. What are the best practices and so on. We very briefly talked about symbolic execution, but symbolic execution and fuzzing is actually a huge area of research. So if you're interested again more in these aspects of things, still also very hot area of research. So you can always read more materials about this. Yeah, these are some of the examples. And another thing that we didn't really have time to discuss was network security. This is mainly a more established and more traditional way of the way that we're thinking about security. I mean, there are various different threats to network, and it's also one of the key elements of securing the system, because network is also, one of the ways of, intruding and attacking a system. Wiretapping, impersonation, attacks on the message integrity or the confidentiality of the message, denial of service attacks, and all those different things. These are different possibilities for attacking the network. And network is also kind of like similar to security. It has various layers of abstraction. You can attack a network at the physical level using, for example, side channels attacks or fault attacks. You can attack at the protocol level and, for example, use something like the log4j vulnerability in order to extract things. And then you can also, attack at the algorithm level, for example, if you manage to find bugs in the implementation of the cryptography methods and so on. So it's really for the network is also an understanding of the entire layer, entire stack would be very helpful. So network security is really indeed a cross-layer issue that we need to think about it at every single layer. Some major issues in modern systems. So I mean, all those traditional issues, it still remains, unfortunately. But what we are seeing so more and more these days is, of course, internet security is one of the key issues. We still, needs to figure out the issues with the browser and the way the internet handles, things. Introduction of IoT and wireless systems has opened up a new, range of issues and attack vectors. So, trying to make sure that new protocols such as 5G or things like LoRa and etc., these are also secure at various different layers. That's also another issue in network security. And of course, another thing is that kind of like, becoming more and more important these days is privacy and tracking, since that most of our devices that are all mobile and are with us can now have the capability of connecting to the internet. Now there's there's a new door and new possibilities for all sorts of privacy and tracking issues that we're facing today. So that's also another line of research these days of what is privacy in this domain and how do we fix this issue and how we can benefit from being constantly connected to the open internet without facing these issues. So these are very interesting. Again, there are policy involved, there is technology involved, there's pure networking involved. So there's like a combination of many different disciplines that works together in order to fix this issue. Another line of research that we didn't really talk about was, distributed systems and blockchains. We kind of like very briefly talked about cryptography and the main basic blocks of the cryptography, but we really have the chance to say that, how cryptography can be used, for example, for creating blockchains and how blockchains can be used for creating things like cryptocurrency or smart contract and so on. There has been lots of interest in this 5-10 years ago. The interest has been renewed recently just because of, cryptocurrency is always like very interesting, scenario and very interesting technology because of multiple different reasons, mainly political reasons. On top of that, secure supply chains is also a new and interesting area of research. This supply chain could be supply chain of, for example, electronic manufacturing, as I described, for example, last week about building a chip, but it doesn't necessarily have to be about electronics. It could be supply chain of, for example, making a car, right? So we want to be able to track every single, components and equipment that being used to build the system. And to track that supply chain, we can also use something like a blockchain, right? So blockchain could be used in many different aspects in order to make sure that the system is secure and nothing bad happens to the system. And there are various, challenges for this. The development of the entire ecosystem is still a challenge. So how do we build an end-to-end distributed system is a challenge. Of course, there are attacks to the systems as well, so we need to be careful and make sure that the system is secure by design. I'm sure that many of you are interested in blockchains. Anyway, so if you're interested, definitely take a look at current challenges, how we actually build a blockchain. I would say you have like 80%, 90% of the knowledge required to understand how blockchain works. Probably some of it you can just read a little bit more about cryptography, but other than that, you should be able to pick up what exactly blockchain are and how they work. And one last thing that we didn't really have time to discuss was malware analysis. So what is malware? Malware is generally any sort of piece of software that is designed to create some harm to the system, right? So anything that kind of cause some damage, whether that's a physical damage or whether that's stealing some information or data from your system, that considered as a malware. There are various models of malware. There is viruses, there's worms, there's Trojans, there's ransomware, there's bots, there's adware, there's spyware, rootkits, fileless malware, and malvertising. So very different, area. I wanted to have one dedicated lecture for malware, but we didn't have time, just because the way that the class progressed. So I'm just very briefly, I'm going to talk about these things. So viruses is just a traditional, piece of software that can create some damage to the system. The damage could be things like denial of service, could be confidentiality. So it's nothing but those three things that we said before: integrity, availability, and confidentiality. Worms is also very similar to viruses. The difference between worms and viruses is that worms is kind of like a piece of hardware, piece of software that is designed to spread itself into a system. So typically what we have is worms, gets inside one computer, but it's designed to automatically and without the knowledge of the users of that system to just spread itself to entire network of devices. So usually worms is designed as you can think about worms as the the initial basic block of a large scale attack, where you manage to infiltrate one of the devices, you use a worm to actually expand it to multiple other devices. Then the worm could have some sort of a payload, which could be, for example, a virus that as it's spread around, then for example activate that virus. And now instead of like having one computer infected with that virus, now we have a huge number of computers infected by that virus. So that's the difference between viruses and worms. Trojans, the difference between Trojan and viruses is that in terms of impact, they're the same. The difference is that Trojan is kind of like a piece of software that it does what it's supposed to do, but on top of that, usually does something malicious. So for example, you download a program and an application in your cell phone, for example, you start using it and this application is supposed to do something. It does those things for you, but as it does those things for you, it's also, for example, collecting some additional information or sending out those information to somewhere else. So it's like a Trojan horse in some sense. Ransomware is it's another piece of malware that these days actually becoming more and more popular. What the ransomware does is basically one way or another, for example, through a war or through something else, it infiltrates the system. And what it does is basically just encrypt your entire or piece of your memory. So what it does is basically, it does nothing but just reading things off of your memory and then start encrypting those things and just writing back those information into your memory. So what happens is that after a successful ransomware attack, most of your memory, or at least part of your memory, is encrypted, and the key is only held by the adversary. So you can no longer use your system because your information is encrypted. And in order to decrypt that information, the adversary typically asks for some ransom, for some money. And if the victim pays that money, typically the attacker decrypt the information, and the user can normally use the systems and continue using the system. So the information is not destroyed; it's just encrypted. And in order to decrypt it, usually the attacker asks for some ransom. Then it sends the encryption and decryption key, and the victim can basically decrypt the data. So that's one way of attacking the systems. Instead of attacking the availability of the system, this way they can earn some money as well. And there are actually lots of real attacks these past few years. For example, lots of hospitals in the Atlanta, Georgia, has been infected by ransomware. There are lots of government level database systems in the United States actually has been subject to ransomware in the past few years. So it's very serious attacks. Bots or botnets is basically this idea of turning one device into some sort of a robot or bot so that it can be synchronized and controlled by some central adversary in order to launch a large scale attack. So this is typically used for denial of service attacks. And the idea is that we want to, instead of like sending, in order to have a successful denial of service attack, we need a large number of devices to do one thing all at the same time. And in order to give access to those large scale number of devices, typically what you need to do is kind of like create and find those bots. So for example, these days, given that there are lots of simple IoT devices existed in the network, people have found ways of hacking into all these devices at the same time and controlling them all at the same time. So then what you can do is that, think about this, that you have an army of millions or tens of millions of these microcontrollers or IoT devices all connected to the internet. And what you can do is now you can, direct them all at the same time to do specifics. For example, they all send a request to a specific server, and that way you can bring down that server, right? So the most famous one is this Mirai botnet attack, which actually attack Bank of America, Netflix, PayPal, all those large, high profile services all at the same time. And this way they can bring down the services, and that could create lots of problems, right? Especially this could be used, for example, again at the state level in order to attack one country or another country. Botnets is usually one of the key ways of doing that. Then we have adware and malvertising. The difference between these two is that the adware is basically this piece of software that sends you ads that you don't want to see. And the malvertising is this ads that look normal, but when you click on it, you usually infect your system. So for example, so you get an email that you want something, you click on it, and clicking on it is basically installing a new malware in your system. So malvertising is that. Adware is just basically a piece of software that gives you ad over and over. Then there is fileless malware, which is basically most of these things that we discuss in this course, in some sense, is a fileless malware. So for example, if you do something like buffer overflow, it's in some sense, this is a file. It's not a file that's infect your computer. It's actually a series of bugs in your systems that's infect your computer. So for example, as I said, buffer overflow is an example of something like a fileless malware. And the rootkit is basically similar again to viruses. The only difference is that the rootkit is typically something that gives you root privileges into your system. All right. So that's typically the difference. And finally, is something that's spying on your computer. It's collecting logs on your system. So it could be part of the virus. It could be part of the Trojan. What it does is basically, recording some information, some private information of your system, and sending it out to somewhere else, or recording it and then it's downloadable or something. So it doesn't impact your normal application or normal execution of your system. What it does is basically sending out this information and logging that information. All right, so that's kind of like the glossary of different types of malwares. Any questions here? All right, so let's have a quick break, and then I'm going to talk about what we should do with malwares in our systems. Maybe until until 3. All right, let's continue, guys. So now we talked about malware analysis. The question is, okay, what we can do in order to prevent, to defend against malware. There are two major ways of defending against malware. The number one way is prevention, of course. There are software or memory protection mechanisms. The main solution is using the best practices to avoid malware to be installed in your system. Generally, malware needs a way to penetrate into your system. So, and if you can find a way to avoid it, then you can make your system secure. Simple examples is like don't open emails or files that you don't know. Don't click on things you don't know. If you are using a specific network, make sure that all the messages is right messages and all those things that probably some of you know. So there are lots of tutorials when we're usually talking about security practices in different companies. Typically, this is one of the main ways, the main things that's covered on those tutorials is how to avoid malwares. All right, so that's number one. The second thing is detecting that your system is actually attacked by a malware. And this is usually what's called a malware detection or anomaly detection. So what happens is the idea here is we need to kind of compare the current state of the execution with some ground truth. And if we see that there is a significant difference, there's an anomaly in the execution of the system, then we are saying that this is probably an anomaly, and this is what we need to stop our execution, right? So basically, you can say that our execution of any software or any application is either it's what we are expecting and seen before, or it's kind of like doing something else that we haven't seen before. And if that's the second case, then we are typically say this is an anomaly, potentially this caused by a malware. So we need to do proper actions. Those actions could be stopping the system, notifying some other level of system to protect the systems, and so on and so forth. And so that's one way of doing this, is basically anomaly detection or malware detection. The second thing is basically what these antiviruses does, which basically looking for a specific signature of abnormal behavior, abnormal software. It routinely scans your computer, scans your memory, content of your system. And if the pattern that you're searching for matches with some known database of potential threats and viruses, they will find that, they will quarantine that, or they delete that, with whatever they can do with it. All right. So the idea is that instead of on the runtime and dynamically search for this, it's kind of like can scan through your system and tries to find those patterns. Of course, antivirus is kind of like more of a reactionary thing. So the attack has happened first. We should know what the pattern should look like and then find those. Anomaly detection is something that can even be applied to something that we haven't seen before. So it can be a better reaction in terms of protecting the systems even against things that we haven't seen before. So we typically call this zero-day attacks, something that from the day zero we can protect the systems. Whereas for the antiviruses and scanning systems, we have to first see and know what the signature of that attack should look like, and then actually propose solutions for it and find those solutions. All right, so that's the detection. Malware analysis. Malware analysis, one more thing to say, is that can happen at many different layers. There are malware analysis at the hardware level, which basically looks at features in the hardware, including different instructions, behavior of the system, and so on and so forth. There are malware analysis that looks at your power traces or electromagnetic emanations, try to detect that. And there is malware analysis that can look at the network packets and try to see if there's an anomaly or network packet, and this way they can detect that. And there are anomaly detectors that works at the software operating system level, looking at the system calls or the instructions and things like that. So at any of these levels, you can have a malware detector. You can have a multi-layer malware detector, which looks at all this information and then make a decision. So generally, nothing prevents us. So anything that we can monitor and we can use as a ground truth can be used for a malware detector. All right. And of course, another key area of research is creating this evasion malware detector. I think one of the papers that we're going to discuss on Wednesday is about this, that assuming that we have a malware detector that tries to see an anomaly in the execution, can we craft another malware that's kind of like fool the system? So it's kind of like a similar to the idea of a certain machine learning. Can we craft a system that, knowing that this is the algorithm that's going to do analysis on this image or this input or this record, can we fool that system in order to evade that? So malware evasion is also another key area of research from the attacker's perspective, basically. And the final thing that I want to discuss, I think that should be the final thing, is hardware security and supply chain. Again, I very quickly last week I discussed this and described the issues, but the trend and what we're seeing is that we are moving toward what's called a secure by design approach, where we want to build hardware that are secure by design. The sheer number of side channel attacks and trojans It's kind of forced many of these designers to think about this. And as I said, this is also part of the larger political game that happens in the world right now, where we can no longer trust other countries to build a piece of hardware for us. So it's also like, lots of interest in bringing and, localizing things that we in the past we always build it from, we build it offshore basically. All right, so kind of like, summarize things that discussed in this course. So the key message is cybersecurity is basically one of the key challenges in modern era. And the reason for that I kind of describe as we are more and more rely on computer systems. This connectivity and accessibility, unfortunately, make it much more easier for attackers to attack our systems. And so this is like, these two things that we have more critical information, but on the other hand, have more devices and more opportunity for the attackers. These two makes the, the opportunity for the attackers to make us less secure, right? So we really need to think about sorry about that. Okay, less secure. So that's why it's kind of like, security becomes this pressing issue that we need to think about. And then the other two things that we kind of like really hurting us has been the negligence on thinking about security as the priority, which, as I said, we are moving toward the direction that this is no longer an issue. And still, because of this, we are lacking lots of policies at the law and governmental level on this. So we still don't know what's the best way of building a secure system. On the privacy side specifically, this is a huge issue because privacy is this very brand new thing that hasn't been around for maybe 10 years ago. So we need to really come up with solutions for and policies with that in the first place. And the final thing is kind of like a course like this would help is lack of proper, education on this. Knowing what exactly are the issues is one of the key challenges that we are facing with cybersecurity. So the good thing about courses like this is actually just spread this knowledge, and you guys now know what are these issues, and then you hopefully can educate others about this as well. All right, so a few things about the course. Final projects due next week, right? So check out the CampusWire post on what you should submit. Some of you need to submit video, some of you need to submit code, some of you need to submit reports. The survey for the class, don't forget to fill out that. I think the last time I checked, we were around like only 30%, so we need much more than that. As I said in the CampusWire, if it gets up to 75%, I'll add 5% bonus to everybody. So try to, not only yourself fill in the form, also encourage everybody else to fill on that form. And I'm particularly very interested to get your feedback on what you liked about the course and what you didn't, what you think it worked and what it didn't, which component you think it was necessary, and which component you think could have been made better. So go through different things. I also describe in CampusWire and tries to give us, feedback. That would be very valuable because, we keep changing the format and on upgrading and improving the course. So any feedback from you guys will help us to have a better course next time around. So in terms of final, I think since to just give you the same time as the project, I decided to release the final on Wednesday of next week, and then you will have 3 days to submit your final quiz. And you only need to take it if you don't do the project. So if you're doing the project, you don't need to take it. It will be again time 4 hours, 30 minutes, very similar to your previous quizzes. So just take it whenever you can. You have 3 days, so hopefully that's enough window for all of you to take it. Any questions? Okay. All right, so what next? If you're interested in doing any research, if your project gets into something interesting and you want to continue working on it, contact me. If you want to uh, do maybe a better literature survey or an SOK paper, contact me. Usually these things, if you do it properly, can lead to a publication. So if you have time and interest, you definitely can contact me and we can talk about this more. Uh, uh, there are lots of security competitions these days, capture the flag events, workshop events and things like that. If you have seen something that is interesting to you, you can always reach out to me and I can try to see if there are other people also interested and we can always, assemble a team. I'll also send out information to various groups, EC Gap or HKN or IEEE if I'm looking for people for joining teams. So if you're into these kind of things, let me know and be in contact with me and we can always find something for you. All right. Uh, so we have to talk about the quizzes. And I think that's it. So for now we have a little bit of time so I can go through quiz 1, quiz 2 and talk about that solutions. But before that, let's see if you have any questions about anything. We good? Okay, so let me stop sharing for a minute. And let me open. Okay, so this was your quiz 1. As I said, when I was grading it, I mainly graded for the effort, not for the completeness. Uh, so question 1 was talking about an autonomous driving system. And as I said, we wanted to check whether you have this system level and machine learning level of thinking about this problem. So machine learning, as I said, throughout this course is nothing but a specific piece of software or piece of system. So nothing really differentiate machine learning from any other systems. The only thing that differentiates from machine learning is we can think about the machine learning and weaknesses in the machine learning as a piece of software, and then think about how the adversary can utilize these weaknesses, right? And that's where the entire field of adversarial machine learning really comes into the play, right? So when you're talking about threat model, you have to think about what are the attacker's capabilities. As I said, I really didn't looking for a specific answer. I was just reading your answers and trying to see your way of thinking. For autonomous driving, of course, where we are in the wild, so nearby devices could be potentially a threat. There could be sensor threats. There could be, adversarial samples all over the road. There could be attacks within the system itself. So for example, there would be a rogue passenger that tries to infiltrate with the systems of the autonomous driving. So that could be also an issue. Some of you mentioned that. So these are the things. And then of course, if there is some sort of networking or cloud computing component, that could be potentially an attack vector as well. But yeah, generally these are the things that kind of that. Potential solutions for all of them. I'm not gonna go through them, but generally exactly depending on which of these attacks really we extensively talk about this. And as I said, the for every solution there comes a cost and there comes some overhead. So you have to be very well aware of not only these are the solutions, but exactly know if, for example, we do this solution or that solution, what would be the cost. So the main message I want you guys to take from this question is, first of all, think about like, potential attack scenarios. And as I said, be as general and generic as possible. But also think about this, okay, what are the solutions for this and whether the solution makes sense. And when we're saying that whether the solution makes sense or not, we're not talking about, obviously, we are not only talking about whether this solves the security solution, which of course it has to be, but also whether this impose significant overhead to the systems and what that overhead would be, right? For example, as I said, like, uh, when we are putting this in the context of, for example, a small constraint system, such as like a startup company or small company or mid-sized company, this cost becomes so important that even if the system is not secure, some companies actually go with that option because they cannot really afford to have a system that doesn't perform well. Because generally, unfortunately, there is this notion of people really understand, for example, what MPG is, but don't really understand whether the system is, for example, vulnerable to adversarial sampling, right? So if you want to, sell some product, some autonomous driving product, it better have to be, costless, looks nice, right? Have some convenience. So people usually choose convenience over security. So you have to be very careful about that and don't sacrifice convenience when you are coming up with your security solutions. Any questions for this question? Any questions for question one? Or any comment? Okay. Yeah, and then so basically what I was looking mainly for, well, like what you discard and what you keep, it really depends on the strategy. I'm hoping that you kind of like, after seeing this real world attacks, now see the value of security, so you won't completely ignore security. As I said, 10 years before, maybe that was the answer, but now we need to at least some basic notion of security in our system. And the reason is actually, it's not just security because it's important, it's actually security at the end of the day is an economy. So for example, if your system is being attacked, then you no longer you can sell your product, right? So it's not just, oh, we should be worried about security because of for the sake of it, but it's just a economical choice similar to any other choice that you make for your product, right? So if your system is being attacked, it's not private, and this information is leaked, there are some real hackers that get into your systems and actually impact your systems, that directly impacts your success in the market as well. So that's why you have to care about security, not just because there's a potential for an attack. All right. So that's from question one. Question two was kind of more an actual, not less open-ended description, but it's more of like an actual, writing things. I think the OT and GC, most people already figure out what to do. Of course, most people didn't really follow the pseudocode, but that's probably because of the lack of, proper, computer science background in some of you. That's all right. The major problem we've seen was in part C. So Garble circuits, it's an algorithm, it's a protocol, all right? And Garble circuits is applicable to a specific circuit, all right? A circuit is defined as something that has number of inputs, it could be 2, it could be 4, it could be anything, and number of outputs. And usually the relationship between inputs and outputs is defined by some sort of truth table, right? So that's usually the way that we define circuits, all right? And usually we use it as gates. So that's typical way when we are designing digital logic. We are putting things into gates and then add gates together to create a circuit. In order to see how any problem can be mapped into Garble circuits, you have to understand that complex problems comprise of multiple circuits and multiple gates together. So for example, for the millionaire problem, the problem is basically just a comparator. And a comparator, if you look at it if you look it up into the internet, you will see is basically a combination of some NAND gates all together. And exactly how these NAND gates are connected to each other It's not an important problem for this course, but you have to just know that any problem such as linear problem is a problem of combination of gates, all right? So what you need to do is basically, you know how the oblivious transfer works, you know how GC for one NAND gate works. Then after that, the algorithm is basically an algorithm of how connecting these gates together. So you cannot repeat things that you said here for like a 4 input and say, okay, this is my garbled circuits. That doesn't work because here we just use it for a NAND gate. So you basically have to say how a comparator is designed by a bunch of NAND gates, and then write an algorithm that says, okay, this for NAND gate number 1, number 2, number 3, these are the things that we do. All right. So think about OT and DC as your basic blocks, and essentially the next step is any algorithm would be a combination of NAND gates and their connections, and then I'm going to just keep calling this GC and OT in order to solve that problem. Does it make sense? So you lose some points if you don't do it, if you just use GC for the third part. And that would be, that was like a good portion of you. I actually did that and lose some points there. Any questions about this? Okay. So the third question was mainly about privacy. So, lots of these interesting systems that we're gonna incorporate in our lives, including things like, cashierless, shopping and these things like that. These are great and definitely improve our quality of life. But the flip side is just because everything is being monitored using computers, all of our gestures and all of our activities also will be, monitored and recorded by them. And as I said just today, that because of the lack of those policies of like what can be recorded and what cannot be recorded, usually these companies these days use this information because, of course, I mean, if don't anybody tell them to not to, why would they, right? So they collect this information and they can do two things with them. They can either infer some information and sell it to other companies. So for example, say this many number of people are, for example, purchasing this product, maybe young people only purchasing this product or old people purchasing this product, and then sell this information to the company that's building that product, right? And that could help that company to get some insight about this activity. Of course, this is a convenience and quality of life improvement for us. But on the other hand, there could be a valid argument that somebody may not want people to be able to track their shopping habits for any reason. So that's where we kind of like the thread model in this case kind of comes into the play, right? So the privacy of various things. And as I said in the course, the attacker may not be just the service provider, it could be the users as well, right? So for example, think about multiple companies that providing the service. If one company can kind of figure out what the other company is doing, they can actually improve their system and have a competitive advantage. So stealing information is another way of doing this. And of course, during the training, how we can steal the information is another way of doing this. One thing to mention is that when we are talking about thread model, you have to describe what is the issue. It shouldn't say, okay, the thread model is, for example, membership interest. That's not a right answer when somebody asks you what is the thread model. When we are talking about the thread model, you should say what are the assumptions, what are the attacker capability, what are the things that are trying to be stolen, and what are the things that we don't think will be stolen or not important, right? So the right answer to what is a thread model is this. Is not listing a number of different attacks and saying, okay, this is the threat model. All right. And the final question was a basic crypto question. So, of course, I think all of you solved the puzzle. The reasons that Enigma machine was not secure was it was basically more of like a one-time pad. It wasn't a many-time pad, right? So the semantic security aspect of things that we extensively discussed hasn't been found. Another key area was like, not having the notion of like complete randomness. So we kind of like map things to the same domain. And for example, we can do dictionary-based search, as you probably have did. So you kind of guess what's the correct word should be, and based on that, find the mapping. Another thing that you probably did was kind of frequency matching. So for example, A and N and E, these are more frequent. So probably those, you can just look at the frequency and say, okay, whatever new matched or new mapped word is, one that has the highest frequency, that should probably be A, or very likely it would be A, and so on. So basically what you did was, with using these different tricks, you reduce the search space, and after that becomes an easy guess, right? So after you kind of like reduce the search space, you finally manage to make a guess. The semantic security is trying to solve this issue, right? So saying that, first of all, it has to be completely random, the distribution. If you encrypt multiple words, each of which should be exactly, should be encrypted differently using some sort of initialization that is random. So if you, for example, encrypt one character multiple times, the resulting ciphertext would be different. So in this case, you cannot really rely on frequency analysis and so on. So these are the typical things that semantic security actually trying to address. And then suggest a method to create a semantically secure cipher for this machine. So we extensively talk about stream ciphers and block ciphers. Block ciphers are usually more useful and more effective, just because it's easier to implement. Things like AES is actually the ones that's very extensively being used. So the solutions that you probably can say was, using something like a block cipher such as AES or Cha-Cha or Blake. There are many more different possibilities for these things. The most famous one is obviously AES. All right, so that's the answer to your quiz number 1. Any questions here? We're good? Okay. So let me see if I have quiz number 2 as well. Maybe go over that. What time is it? Okay, we have time. Okay. Okay, so this was your quiz number 2. So for the Starship delivery systems, I kind of go through it today. So you have to think about the sensor. So there are multiple different things that the sensor can do. You can always do the spoofing, right? So you can have another source that's kind of like impact your main source. So if you have a camera, there could be maybe another source of like electromagnetics or acoustic or something that creates some interference, right? So that could be one example. The other example could be things like such as creating faults or creating adversarial examples. So although your camera, for example, is looking at a specific object, the way that we are creating this object is deformed or adversarial, such that the system gets an incorrect information. So basically what we are doing is we are changing the physical world in some sense, either changing the objects itself or creating some sort of interference to that object to create this to this issue. So as I said, this is actually a very interesting area of research. There are different things that at the physical level people are thinking about. What can we do to kind of combat both of these issues? On the local processing side, many different examples. Fault, for example, is one example. One thing that can be done is that maybe we apply some laser or some high energy to the systems and cause some bits to flips. That's one example. Another example is something like a physical side channel attack in order to, steal some information from the local processing. So that's another example. On the network side, there are various things that can be done. Man in the middle attack would be one example where the local process has to send the information to a specific, node in the cloud, but during the process, somebody else also record this information. So that's kind of like, stealing the confidentiality. The other thing that can happen is spoofing this communication so that the communication actually doesn't reach to the intended target. So in the kind of this case would be a denial of service attacks where the sensor can no longer send information out. There could be also another things that impact the confidentiality. So for example, we record this message, tries to break the crypto algorithm in order to get the information out. So that's from network side. For the cloud side, digital side channel attacks is one key issue. Attacks that do stealing of, for example, the model on the cloud from the device side and user side could be another. For example, let's say, for example, somebody wants to see what sort of routing algorithm the Starship is using. They might be able to craft some adversarial samples in order to do some sort of like a model extraction for the systems, right? So these kind of issues could be there as well. For the actuation, the attacks could be either actually applying some real blocks or issues for the starships, or there could be things like reverse engineering systems or changing the internal of the system so that commands doesn't normally or correctly change the outcome of the system. For example, the goal is for the starship to turn right. We change things or create faults and make the system to turn left. Things like that can happen in the actuation. All right. So these are kind of examples. Definitely, there are many more examples. I'm sure you guys have come up with, but kind of is around this round. Any questions here? Step-by-step pseudocode for a prime and probe. I'll probably just post this on Campus Wire, but as you remember, there's three phases, right? It's the priming phase where the adversary just finds what is called an eviction set, which is a number of memory addresses that all happens to be fitting into the exact same set. The adversary access all these memory values one by one. And the goal is just fill the entire cache set with the adversary's data. So that would be the first step. The second step would be the waiting phase, where the adversary just waits for the victim to access or not access that cache. So just finding the right time for waiting is important. Then there would be a probing phase, which the adversary, again, access those memory lines one by one and measure whether this was a hit or miss. If at least one of those accesses were missed, it means that during the waiting period, the victim has accessed the cache. So this means that the adversary and the victim has accessed the cache, and the adversary can translate this information to whatever knowledge that he or she has. So for example, let's say if the key was 1, the cache has been accessed. If the key was 0, the cache has not been accessed. So that's information of whether cache has been accessed or not accessed can be translated into the system. So kind of looking for something like this. Let's see how you guys did it. Question number 3 was the dynamic root of trust. So as I said before, the key challenge in our computing system is having a dynamic root of trust, because the static root of trust was actually our TPM. But what we wanted to have is something that we can basically, during the execution, we can either decide to trust and add or not add, right? So what I was looking for is basically this mechanism for how to build, how to fully load an operating system or the beginning of a trusted execution environment to talk about hashing and how we do the attestation and how we start with keys in our TPM, and then how we manage to actually load a full program. So kind of like the notion of this chaining and how this exactly works, that was I was looking for. And when we were talking about the measuring, so as I said, measuring was this concept of the attestation. So basically measuring means this program that we send a challenge and get the response. The challenge typically is like a list of addresses of the memory. And the response is computing this hash over those values and sending back those hashes. And then what in order to establish the trust, the verifier, the one that can be trusted, get this hash value, also locally computes this hash value, and then compare these two together. If they match, it means that the system can be trusted. So that's the notion of measure. Any questions? And then steps for launching an ROP attack. So ROP attack is very similar to the buffer overflow. So the first steps is, of course, finding a vulnerable, memory activity that can overwrite the things in the stack. The first thing is that you need to, overwrite your return address. On the normal shellcode, attacks, your return address will pointing somewhere else into your memory, somewhere else. For return oriented, what you need to do is, instead of planting your payload somewhere in the memory, you actually need to reuse the code that exists in the same. So there is an offline phase for finding the gadgets. Usually there are compilers for finding these gadgets. The gadgets is basically a series of codes that ends with the return. And when you find those, you have to find the beginning address of those gadgets. Then you find a chain of these beginning addresses. You put them all together and you create this list of return addresses, address 1, 2, 3, 4, 5. And then all you need to do is basically pointing this address to beginning of this chain. And what happens is that after that, automatically the rest will be executed. Why? Because we are just putting everything here into the stack. So we start some instruction, then we reach to a return. Where this return goes to the beginning of this next code, because that's where your return address is currently. So then these instructions executed, then return goes to this. So basically you're just executing a normal program with just some return in between. But since you chain all these return addresses into your stack, it just pops them one by one until it reaches to the end. And then after that, you can just jump back to the original place that you were supposed to jump. And this way you can just run any arbitrary piece of code that you want. The only requirements is that you have all these gadgets ready, and that's usually an offline phase. You can look, for example, into libc as an open source header file, and you can find all those gadgets. And there's also extensive work that tries to find that for you. All right, so that's it about the ROP. As I said, the only difference is that in normal buffer overflow, you jump from here to some payload, some shell code. For ROP, you jump to a series of gadgets and chain of return instructions. All right, and the advantage of ROP over normal shell code is that you don't have to plant anything. This code already exists. All you need to know is where is the beginning of these addresses. That's all you really need, and then you can scan this and find that beforehand in an offline phase. All right, so that's it. Final questions also. Thanks for all the suggestions. If I have time, I'll try to actually publish this so all of you can actually use this database of good restaurants in future. All right. So that's about it, I think, for today. I have nothing else to cover. As I said, on Wednesday, we're gonna have the paper presentations. And then I'm gonna also quickly talk about projects and finalize that. All right. So that's it, guys. Thank you.